Chapter 1, Free Body Diagrams and Normal Stresses. First of all, we need to go by a equilibrium definition in terms of mass, and that's the resultant of all forces and moments acting on a body. It should go zero in terms of mass to say some structure or piece of machinery is in equilibrium, and that's summation of forces at x goes zero, summation of forces at y goes zero, summation of moment about any arbitrary point in the free body diagram should goes by zero to say that's in equilibrium in terms of mass. And in terms of conceptual, in the concept, a body is in equilibrium if all forces and moments apply to it are in a balanced condition. So to approach problem solving related to free body diagrams, for example, what you can see here is a marine crane, and if we just want to know what are the axial forces in the crane, so we can simulate it by our model here and then put it in a example to see how to solve the problem. So to approach the analysis of free body diagram, we need three stage to solve the problem. The very first is drawing accurate free body diagram, then developing moment about any arbitrary point. For example, here point A is a good a starting point because it cancels out two vertical and horizontal component of pin A. And then calculation of forces, and as soon as you have the forces, you can go by dividing the force over area give you the stresses either in tensile or compressive formats. Let's put it in an example. So if we do have a crane, a marine crane, if we do have a marine crane and like link CD is shown with a uniform cross section of 50 times 150 millimeters. This is the link CD, and this is the whole configuration of the crane and the hanging box from the top of the crane. And then we need to determine the normal stresses in central portion of the link CD. So we just need to go by calculation of sigma CD. So if we know what force CD is and divided by area of CD, which is provided in problem statement, we can have the stress in our member. Let's see how it goes. First of all, we will draw our free body diagrams of the forces acting on the crane, including the box. And by having so, and if we just calculate the hanging weight of our load, so that's 80 megagram, the weight of loading, times the acceleration g in SI, which is 9.81 meters second square over second square, and it gives almost 800 kilonewton in terms of hanging W. And then by applying a moment equation based, for example, in about point A, which cancels out the two component of forces at A, we can have a reach to a relation between force CD, which applies here, and the other one, which is W, based on their distance from the point A. So it gives us FCD is a 28 over 15 times of W, and it gives almost 1500 kilonewtons. As soon as we do know what FCD is, by simply, and also BC is a tensile force, sigma BC hence is a force of BC over area of BC, which we already calculate, positive because of tensile, 1465 1465 or times 10 cube based on Newton over 150 times 50 10 to negative 6 square meters, and it gives you 195.3 10 to 6 Newton per square meters, and that's nothing but a positive 195.3 megapascal, and the positive stands for membrane tension. In our second example, you can see two horizontal 5 kilopound forces applied at to pin B. This is pin B connecting the two links of AB and CD, and all of a sudden two 5 kilopounds uh, force to the drags the pin B to the all the way to the right. If we know the diameter of the pin, if we know the thickness and also width of the legs, and also the diameter of the pin is provided to be 0.8, so that says my pin diameter is 0.8 inches. Determine the average normal stresses in link AB and link BC. So again, we do need to calculate the forces. First of all is drawing an accurate free body diagrams for the whole structure. Then as soon as we have the free body diagrams, we can get our forces from it, and force over the cross-sectional area gives us the stresses. So by applying law sine, you can create this triangle. I do have a 60 degrees here, and then 45 over there. If I just add these two forces together and drags down and show them in a resultant force over here, and how that goes, by drawing a free body diagram of forces, developing the force triangles to apply the sine law, and then calculate the forces. So if I just add up, this is pin B, and I just add these two forces together and put it as a 10K over here. Then to develop or create my triangle, I just shift it down here to develop my triangle to get benefit of law sine. In law sines, it just says FAB over sine of 45, FAB over sine of 45 is equal to FBC over sine of 60 is equal to the resultant force of 10 kilopounds over 75. So it says as soon as you develop this triangle and applying the law of sines, you can easily get the two unknowns of FAB and FBC. So it gives us FAB equal to 7.3 kips and FBC 8.96. Now simply by dividing the forces over cross-sectional area, we can get our stresses in both members. So as by closer look to the configuration, you can easily see 2 5 kilopounds drag the pin B to the all way to the right. So if we just take pin B out of the diagram, it just gives a tensile pin. The same force applies to link AB. Hence, link AB is a tensile member. That's a interesting result for us, or important result for link AB. Then, as soon as we do know that link AB is under tension, we need to go by net area, or A nets. And what net cross-sectional area is the thickness over here, the width of the leg AB, or link AB, minus the diameter of the pin which is provided in problem statement, times the thickness of the steel. So that's nothing but 0.5 inches. And if you calculate the net cross-sectional area, it's 0.5 inches squared. Then as soon as you know the net area, which is 0.5 inches squared, we already calculate FAB is 7.3205 kilopounds, and if you divide the two numeric value, you get sigma AB under tension, so it's a positive 14.64 KSI, which stands for kilopounds over square inches. Likewise, if we attempt for link BC, so link BC, if link AB by the configuration of forces, this was under tension, and you can easily understand that the nature of dragging to the right forces is it make a compression in link BC. You can also get the result with the free body diagram as well. If you don't have the intuition of that, go by the drawing the likewise what I did for previous part, do for pin B and link BC to verify that's a compressive member. As soon as you know sigma BF link BC is a compressive, you do not need to go by net cross-sectional area, so there is no need for that. Just go by the ABC, which is 8.5 times the thickness of the link, which is 0.5, and it gives you ABC is 0.9 inches square. We already know what our sigma is, FBC is that 8.9658 kilopounds. Our at denominator you can see 0.9 inches square, and that gives you 9.962, and that gives you sigma BC 9.92 KSI, and because sigma BC is compressive, that's a negative 962, which stands for a compression.